In my chemistry classroom, it takes us most of a semester to lay the foundation for chemical change, the reason for chemical change, the reason for chemical bonding, and ultimately chemical reactivity and reactions. And that track starts with Bohr's model of the atom, in an entire unit based on electron location and energy and behavior. And now I've met with teachers who have suggested that maybe the Bohr's model is too simplistic for the average high school chemistry student, that it needs to be more rigorous, that we need to jump right to Schrodinger's model because it is the more comprehensive, detailed, complex, modern model. But I would challenge you that revisiting a model students are familiar with from biology class and holds very specific core ideas in and of itself that can connect directly to that more complex model is going to ensure that our students have more understanding and more time to process and do the critical thinking that's necessary to sort out the why of all of it. Now, as this is lab in every lesson, I hope you're expecting me to bring you flame test. Because if there is a lab associated with bulk parts of your lessons, and a very traditional lab in chemistry is your flame test. Your flame test might be the driving phenomena of this lesson, the whole reason to do the lesson. You might be, if you're following NGSS or some adaptation, breathing a sigh of relief that you have a phenomenon to lean on. But in fact, Bohr's model provides a whole plethora of phenomenon. We can talk about highlighter ink pens, we can talk about fireworks, we can talk about neon signs, and then of course the flame test. I would challenge you that think back to when you were a student yourself, in fact, and your teacher gave you the flame test to do. Could you really see what was happening and connect it to facts that you learned in class? I couldn't, and I would say the average student who is being lectured to and taking notes also cannot. Throwing in phenomenon for the purpose of throwing in phenomenon isn't what a three-dimensional learning strategy is all about. Rather, if we approach it from the perspective of student discovery for what's happening at the microscopic level, we can more easily help students make the connection to that macroscopic level. And that's in fact what I think we're going to see this lesson do here. So firstly, I want to remind you that all of my lessons have been mapped to the three-dimensional standards. They weren't built that way. I wasn't looking at them at the time. I just merely wanted to make science a practice every single day. I wanted observation to drive my instruction, so no student had any reason not to engage. So that every student said, all I have to do is write down what I see, score. I can do that. It's the I can do that feeling that I'm after all the time. And in science, we are lucky enough to have muses all around us. It's my job to bring students the muse, the object to observe. Now, it's also my job to help iron out the wrinkles of what they can't see themselves through in that critical thinking and reasoning, in using their observations as evidence to create inference in the process of analysis. And then, of course, to facilitate collaboration and communication of the results. That's the essence of what every one of my lessons should hold, and I think that's what you're going to see today. So very briefly, I'm going to remind you that our three-dimensional standards, if you do need to follow them, they do only call out one cross-cutting concept that they want us to drive forward for each standard. And for this standard relating to structure and properties of matter, using the periodic table as a model to predict the relative properties of elements based on the patterns of electrons in the outermost energy level of atoms, that is patterns. Now, a couple keywords that get us to patterns there are, of course, periodic table. The periodic table holds so many patterns. And if you're just starting out with these three-dimensional standards, they can feel very overwhelming because you maybe have 5 of them, 5 to 10. None of them call out specific super specific core ideas. There's a couple, maybe 1 or 2 core ideas, maybe 3 for each standard. But you and I know there's a whole lot down in there, especially for chemistry, that we need to incorporate to get to even those core ideas. So properties of elements in the periodic table, definitely a pattern to that. The electron configurations have a pattern within the periodic table. The valence electrons are patterned within the periodic table. So yeah, patterns abound. But when you're planning individual lessons, and so I'm just going to speak to those folks here who might be tuning in because they're interested in planning tips and tricks. It doesn't mean that you're confined to bringing out just the patterns in every single lesson. In fact, we're going to reveal some patterns here in this lesson, Bohr's model of the atom concept that I'm going to present to you. But the pattern isn't in the periodic table necessarily just yet. The pattern is in the data that the students will identify and that I want to draw out from them. They will also clearly see in their activity that there is cause and effect. There's a relationship piece, a huge relationship piece, multiple relationship pieces in this one idea, in this one phenomenon of the universe. Of course, Bohr's model is a model, so we're addressing systems and the models and their parts. Energy is involved when we're talking about Bohr's model of the atom because Bohr's model of the atom was so much more than just orbitals around a nucleus. And that's pretty much the extent that your students know it in biology class. And then, of course, I am saying this has huge implications to overall eventually reactivity because the premise that students are learning here about the relationship with energy and electrons specifically is that they could jump around. And if they can jump around, then they can jump out. And that, of course, starts the whole ball rolling. In terms of science and engineering practices, how your students are going to function as scientists in engaging with this lesson, they're going to develop and use models. They're going to use a simulation model. They are going to analyze, interpret data. Depending on how you deliver this activity, they could actually collect the data themselves, or you could just provide it for them. But data is absolutely necessary for students to cite evidence. There is, of course, qualitative evidence and quantitative evidence. This lesson provides the opportunity for both. For me, I have students do the qualitative and I bring them the quantitative, and I make sure that we're constantly pointing to data. So that's where the engaging in argument from evidence comes in, and also obtaining, evaluating, and communicating information. So let's take a look at the lesson itself. All of my lessons are built upon objectives expressed as learning intentions and success criteria. So we might say today we're learning about the solar system model of the atom so that we can talk like scientists. Always top of mind for me because I want students to come out being able to discuss the lesson with me. Discuss in the future, we want to use the terminology that emerges. Understand why electrons are never still, they're always moving, and determine which electrons in an atom will participate in chemical reactions. Now I want to pause there just for a minute because I've taught with this lesson probably for 3 years before I started tweaking these a little bit, and they do require some updating in my store. I want to show you how those learning intentions are different from what I've just presented this week to my own students. So I can understand why electrons are never still, they're always moving, has become explaining the relationship between energy changes and an electron's position within orbitals of an atom. So the learning intentions slightly give a sneak peek as to what students are going to be doing, but also the why. And what I'm doing now, as I'm trying to more closely align with our three-dimensional standards, STEELS here in Pennsylvania, is the cross-cutting concept. Really, that should be the why of our learning intentions. So in so much as, for sure, this is all day long, cause and effect. And energy and matter and system models. We really want to highlight that for the students. This is about energy from the sun. Everything is made of matter. Matter has atoms. As long as there is light, we have something happening. And then predicting which electrons in an atom will participate in chemical reactions, because I want them to know valence electrons. And so that remains the same. What you can expect them to do is the outline I make for success criteria. And success criteria, I don't see them as what you can do after the lesson, but also what students can expect to do during the lesson. So yes, we should be able to define terms after the lesson, use them. Also maybe not define them, but use them. Edit required there. Observe electron movement in atoms. We're going to do that with a simulation. Explain what the rings around a nucleus really represent, something more than location. Describe how the law of conservation of energy applies to electron behavior in atoms. Now, that's something that I have modified for myself recently that I have excluded because I had to eliminate my law of conservation of energy foundation lesson at the beginning of the year. But I've done law of conservation of mass by this point, a very brief overview. So my students understand no gain, no loss. And we were able to work through that anyway, even though I didn't make it a central goal. However, I did include some success criteria here that are assessment-based success criteria. So not just activity-based success criteria, but also assessment-based. Because on a test, you might want to tell them, give them a picture of an atom with an electron in and ask them, when I zap this with energy, what's going to happen to the electron? They need to be able to predict that behavior. And then finally, to identify the number of valence electrons in atoms. And that leads us right down the path of everything that comes next. Being able to draw models of the atom, which maybe I'll be able to mention today, where the valence electrons are in Schrodinger's model, and how many, and how we find them on the periodic table, and of course valence electrons central to the octet rule. Valence electrons set up in the beginning of this unit is critical to all the rest of it, as I see it anyway. Okay. All of my lessons also contain a warm-up. The warm-up for this lesson is to revisit the timeline, because at this point in my curriculum, my students have explored the basic atom, and as an extension to the basic atom, we dived deep into the nucleus, because that's what the timeline sort of told us. That's sort of what the timeline did. It set up the idea of there's an atom, and then we had people identifying particles, Thomson, Rutherford, Chadwick. And now we can set the nucleus aside and exclusively focus on Bohr, Schrödinger, not so much Heisenberg. But if you have my lesson on the scientists of atomic history, then you have this lesson where students have actually already done this. That is the review. And the preview portion, of course, is that we're going to be working with Niels Bohr. I also include some word walls here and highlighted terms that I'm bringing in from my foundational unit, the pervasive principles unit, these ideas that we're going to constantly be revisiting, the micro to macro idea, atoms, elements, group number, and period have already been introduced, physical properties and chemical properties of substances. Now we're going to be able to see atoms portraying them based on the composition of the atom. The idea of energy also, in and out. Energy needs to be constantly weaved into this curriculum, even though it's not a main player, even though our physics peers get to teach more on that. It's huge, and it can't be ignored, in my opinion. So it's there, even if it's not at the forefront. In the unit I just finished on the atom and its nucleus, also highlighting these ideas that have already been introduced, prior knowledge required, electrically neutral atoms, the number of protons equal the number of electrons, and of course all the parts and where they live, the atomic number as they can map it to the periodic table, and also what it represents. Always including some relevant vocabulary. Lots of times in my lessons you'll see the words and no definitions, and in fact in this lesson I give a partial definition for valence electrons, which simply says the highest energy in an atom, and it takes us back to that connecting piece, which is explaining the relationship between energy changes in electrons. But later on, at the end of the lesson, I'll expose, hey, these are also the outermost, but I'm going to let the students go there. At first, I simply say, you know the orbitals, you love to draw them, even when I don't ask you to. They are the Bohr atom. We give a little nod to the electromagnetic spectrum because that's kind of our phenomenon here. It's the atoms that create the visible light that we see in neon signs, in fireworks, in flame colors. And so at this point in the lesson, it's just a trickle. The main act of this lesson is a simulation where students simply have to press a button. They just press a play button. This atom gets zapped with energy, which I remind students constantly comes in so many forms. Could be the heat in the room, could be the light coming from the sun or the moon or the stars or our lamps, right? Our light bulbs. And they're going to hit the play button. I encourage students to do this at least 10 times. Again, I don't have them record data. You're going to see this data later on. But this is data I've collected. I would say this is definitely one opportunity for you to differentiate for your higher achieving students to collect this data if you know that they can work reasonably quickly and that their critical thinking is to a place where they are competent with working numbers. For me, when I present this lesson, it is in late October, early November. My students are not yet versed enough they feel overwhelmed by numbers, so I don't do that. Also, it would take them a whole period to just the transcribing of all this because I do teach online and they have to do the online systems. But know that this is provided later on. All I'm asking them to do is feel it out. And in so much as I have a artifact for students to complete, this one is very much more of a note-taking form. It's less of a graphic organizer and more of just a series of prompts, that guided inquiry, pointing students to the things I want them to take note of. Because if I give them just a wide open, what do you notice, we're not going to be able to touch on, in an efficient way, all the things that we need to be able to see and do and understand. Things like just basically what's happening, because our goal here in the beginning was understand why electrons are never still, they're always moving, or too soon be modified with explain the relationship between energy and electrons' position. We are going straight to that by saying what happens when the atom absorbs energy, what happens to the electrons, what happens when they're released. Once we get excited, and this simulation refers to excited electrons and ground state electrons, do you agree or disagree with a statement as it pertains to your experience? What about the color of light emitted? What about one thing I love about this simulation, and I have already taught the mole concept. We haven't worked with the number mathematically, but we've taught the mole concept in my foundations unit because so important to remind students constantly when they're learning chemistry. It's never one atom. We have to study one atom for that system and system model idea to portray something we can't see. But when we're connecting the micro to the macro, we have to always be aware that there's more going on here. So there is a function in this simulation where you could play all atoms, and it does look specifically at a neon tube. A neon light tube doesn't necessarily contain neon, the gas, but could contain another element for which there are sextillions of atoms, right? So what happens when you click play atoms? What about solar system model and energy levels? How you feeling about that? And oh, by the way, which is the orbital with the highest energy? Because that's also a goal of the lesson, to identify valence electrons. And we've already said valence electrons have the highest energy. So when students pause to think about that, how it got so energetic to begin with, we're setting up success. Also included in this lesson that I sell online is A little bit of extension. If you have some early finishers, they can go off and complete an activity there, but definitely not a central component of the lesson. When I bring students back, either from independent work or small group work, I do provide them this data. We go through a series of option questions. Now, if the students did complete the activity, and for me in my world, it's difficult to know unless I ask these kinds of questions. I can't keep them open-ended because only a few people will ever, even in your classrooms, only a few people are ever going to be like, hey, sure, I'll tell you. So I would want to see everybody represented. So what happens when the electrons absorb energy? And so I basically just transform all those questions into simple polling questions. But what we can do here with the data provided, and I explained to the students that I didn't ask them to write down the data, but that I wrote down my trial data, and the simulation is random enough to produce something different for every person running it and every trial you do. You can't expect it to come out this exact way. That this is just a detailed description of the results, and we can point to data to support this. So of course, when atoms are absorbing energy, what's happening to their electrons, we're pointing to column 1 where it started and column 3 where it finished, is its excited state. In the follow-up question, what happens when they release, we're looking at that excited state and then releasing back down to the relaxed state, wherein the excited state is always higher than the original and the relaxed state is always lower than the excited state. Yes, that's right. Checking myself there. Understanding again, some electrons are going to return to their original ground state, and sometimes they are not. And we can point to specific data here that's true in, for example, trials 2 and 3, where it goes from 2 to orbital 6 and from 6 back down to 2. But it's not necessary because we see plenty of opportunity where that's not happening, like we go from orbital 1 to orbital 3 and then only back down to orbital 2. Then of course, and the whole phenomenon driven reason for the lesson or phenomenon connection is the color of light. How does the color of light emitted connect to this whole piece? And here, again, this is true of course, we can highlight the data to prove it. Every time this pocket of energy is released, we see purple light. And in multiple trials, 2nd, 3rd, and 8th. Every time this pocket of energy is released, we get red light. And we could see that in trial 1, trial 4, and trial 5. And then we can go on to expand and have that discussion about what happened when you played all atoms. Why do you think this is going on? And something I've added, again, recently for myself that I will be modifying pretty soon for the lesson that I sell is to provide a video. Now, and this is maybe where you want to do the hands-on demonstration, or if you have those tools in your classroom, you have some emission lamps and you have some diffraction glasses, your students can see that main point here. Neon doesn't have to be on neon lights. Could be helium, could be argon. And I think there is one more that he experiments with. This is a really long video that I have to just show snippets of, not the full 16 minutes. No. But then we go on to talk about, well, wait a minute, conservation. If we're not putting out all the energy we put in, if we're not going back to that ground state, what's happening to the energy that's left in that electron? The energy released, instead of going back to orbital 1, it just lands at orbital 2. Then what? And you can have that great conversation where your really bright kids are going to say, maybe it's storing the energy. Maybe it's releasing it as heat or some other energy form we can't see. And then you have the opportunity to introduce another phenomenon, which I, again, recently just did, and that is fluorescence. You can show them the basics of fluorescence, which this video here is a very nice overview of everything they've studied to this point, plus fluorescence, and this idea that you get 2 relaxations, but you have to have a certain type of energy input, and then a really fun video that just provides perspective and the interesting, awe-inspiring everyday world piece of like highlighter ink. Something so simple. Okay, rounding out the lesson, going back to its structure and the model, and this idea of solar system model being same as energy levels. How do they feel about that? And in which orbital does this electron have the most energy? Of course, then getting them to say it's the one in the outside because it had to gain energy to get there. If we're looking, of course, at just a simple model of, say, hydrogen. And then we can reveal, yes, that valence electrons are in the outermost orbital of an atom. And a great exit ticket, if you will, or I used to do this simply as a skill practice. I would call this skill practice. So at this point, we've been through clear goals, a relevant warm-up that also previews the lesson contents, a main activity with task instructions and an artifact outline, a lot of detailed data-dependent analysis there, some phenomenon piece. We need skill practice to make sure that the assessment is going to go well, right? The conventional assessment. In Pennsylvania, we are not yet figured out the Steele's assessment, but I think there's ample opportunity in the videos I discussed there and snapshots even from the video to explain this scenario. As long as you're super always focused on evidence, you're training your students every single day to look for evidence, those are going to go swimmingly. Here, just asking students to decipher, read more models. How many valence electrons are there? What about what we would call core electrons? And identify the atom. That's a great recap also of their atomic number training. But there's also another exit ticket included here that I include in book widgets. And even if you choose not to use the book widgets, then you can just basically sort this out. You got all the information there, the how would you say, intellectual property to recopy it, and that's okay. However is best to use for you. Of course, the link to the digital notebook comes with all of my packages as well. Now, I want to just shout out here at the end a couple of things. I used to do this whole lesson in one period, and it was check off the box. I did that with independent practice, not group work. My school is super interested in collaboration this year, forcing the issue. And so luckily, most of my activities do lend themselves well to that. Group work takes time. So I have finished a handful of lessons this year in one period, a 15-minute period. This lesson did not take me one period. For perspective with group work, I was able to get to this point in the first period. And then the whole second period was devoted truly to discussions about phenomenon, showing those videos, talking about the energy, and relating back to valence electrons. Also, I always do these in Seesaw, but that has changed because my school has changed their focus. So now I'm exclusively using Google Drive for a lot of things. And I just want to remind you that if you also, I know a lot of teachers using Google Classroom and Google Documents. What I do here is I just save the files as a PNG file. So for example, something I want students to do, this one, I would just do File and Save As, and I'd go to PNG and save that as an image file, and then I can go into the background of a slide and change and just pull up the file, and that's how I did this. So no students can move any of my images. They can just use text boxes and write on there. And that's a great way to distribute them as well, though I really love Seesaw if you're going for independent work, and also in a face-to-face environment like you likely have, you have students sitting next to each other. So they could do their own work, but work together. I don't have that luxury. I want to shout out, final parting words, that the advantage to having a full curriculum from whoever that your favorite author is, if you like to lean on the done-for-you stuff, is that you can piecemeal all of their stuff together. So I have a half day tomorrow, and part of my size lesson which I'll talk to you again about soon, I'll be sending to you, the review and preview warm-up of my size lesson has students taking these same 3 models of the atoms and identifying them again, revisiting number of electrons, number of orbitals, but also their knowledge of the periodic table, the group A number and period number, so that they can get to this place where they recognize, every atom can be characterized number of orbitals by its period number and group number by its valence electron number. Now, I used to try to squeeze that into this lesson on size because it's completely relevant if students are going to draw it out. And being able to draw out the model is, number one, an NGSS core principle, being able to work with models, create models. But like I said, I did this way before I knew about those standards. I think this is an important stepping stone to the critical thought that takes you through the rest of all of the electrons unit. No matter what we're talking about, gain and loss of electrons, ionization, octet rule, and bonding, that they can draw the basic orbitals and number of valence electrons helps give them a tool in their toolbox. So where I used to just squeeze this in as an additional activity, I wanted to separate it out now and make it really profound. But because I'm even lower on time than I thought I would be, what I have done is actually for tomorrow, for my half day, set the students out with that activity to basically bridge now what I know about the Bohr model in how it's built, and all the electron stuff, and just be able to draw it as a short day, 20-minute class before we jump into size. And because I have access to the review and preview that's in my next lesson, where my review and previews are intended as a bridge, they're intended to do that formative assessment, to also review and spiral back on old knowledge, but then pull in and connect to the next topic. You can make this mini lesson so easily, where I was able to make a main activity day, drawing models, and a follow-up extra credit activity where students are going to go through a series of drawing and then cite evidence as to which is bigger and why once we finish the size lesson. Just a quick reminder that when you purchase the Micro to Macro curriculum, you do have access to all of the updates as I am adding them in there, where it takes me a little bit longer to do so with the Teacher Pay Teacher products, but for sure they get there in time. Thanks for joining me today. I hope to see you soon and tell you all about my atomic radius related lesson.